Okay, so today we're going to pick up where we left off last time. Now we're looking at the multiplicity of roots. So sometimes a polynomial equation has a factor that appears more than once. This creates a multiple root. In 3x to the fifth plus 18x to the fourth plus 27x to the third equals 0, there are two multiple roots, 0 and negative 3. For example, the root 0 is a factor 3 times because 3x to the third is a factor of this, and that's equal to 0. So that it's x to the third. So there are three separate x's with a factor of, or with a root of 0. So since we have these three separate roots, or these three separate factors with a root of 0, this would be called the multiplicity. The multiplicity of root r is the number of times that x minus r is a factor of the polynomial p of x. When a real root has even multiplicity, the graph of y equals the polynomial touches the x-axis but does not cross it. When a real root has odd multiplicity greater than 1, the graph bends as it crosses the x-axis. So when I look at this now, if I have a root of negative 3, it has a multiplicity of 2. You can see it comes up and it just touches the x-axis and drops back down. This one, it's 0, has a multiplicity of 3 because it bends as it crosses the x-axis. Now if it was a multiplicity of 1, if it was an odd and just 1, then we would not be looking at a bend, we'd be looking at a straight line coming through. But since it is not 1, or since it bends, we know it's not 1. So it's going to be a multiplicity of 3. If we look back at our polynomial that we started with, x to the fifth is my degree, which means there are 5 roots. So I have 2 roots here and 3 roots here, so that's a total of 5. We can't always determine the multiplicity of a root from a graph. It's easiest to determine the multiplicity when the polynomial is in factored form, but we're not always given a situation where we can factor. So, identify the roots of each equation, state the multiplicity of each root. So, whenever I look at this graph now, just by looking at this, and this is used doing a graphing calculator, but you don't have to use a graphing calculator. You could put this into Desmos, and it would graph it exactly the same. You would see the bend in the function. So I see a bend in this root, and there aren't any other roots, right? So since there aren't any other roots, I can look back at this number. Where does it cross? It's crossing at negative 2. So it has negative 2 is a root. So it's x equals negative 2. That's my root. And my degree is 3, so with a multiplicity of 3, since there aren't any other roots in this equation. So there's nowhere else it crosses, which means that all 3 have to be right here. And this bends as it's crossing, which tells us that it's going to be an odd multiplicity. Obviously can't go up to 5 because that would be more roots than are allowed. Let's look at the next one. This is an equation for, I don't know why there's 2 on here. Get rid of it. State the multiplicity of each root. So first, let's look at where it crosses. It crosses at positive 1 and at negative 3. So x equals negative 3 is a root, and x equals 1 is a root. Now when I look at it crossing at x equals 1, it's a straight line. So that tells me it has a multiplicity of 1. It's not bending there at all. Sorry. Apparently I can't spell multiplicity. Multiplicity of 1, because it doesn't bend as it's crossing. Back here, it does bend as it's crossing. So this is at negative 3, and it's bending. I need a total of 4. I have 1. That means my next has to be an odd that's greater than 1. So it's got to be 3. If I took this x equals 1, because that's where it's crossing, and put it back into its form, it would be x minus 1. So remember, we would be setting that equal to 0. Add the 1 over, you get x equals 1. So in other words, if I'm trying to find what this would be in a factored form, this would be x minus 1, and then it would be times x plus 3, just the opposite sign of this, x plus 3, x plus 3. If I multiplied this all out, I would get the same thing. An easy way to check to see if you got your multiplicity right would be to go to Desmos. So when I go to Desmos now, if I enter my original equation in, x to the 4th plus 8x cubed plus 18x squared minus 27 x to the 4th plus 8x cubed minus 18x squared minus 27. Let's see how good my memory is. Plus 18x squared. Close. Not quite. You'll see that my root is at -3 and at 1. It's clearly a straight line coming through here. And now if I take those multiplicities that I found, and I just put those in, x minus 1 times x plus 3 times x plus 3 times x plus 3. You'll see that my new graph completely overlaps the old one, which shows that they are a perfect match. So these two are the exact same function. So it's a good way to check your multiplicity. If I thought it was a multiplicity of 2, you'll notice how my function changes. So again, good way to check. Shouldn't get any wrong on this part of the assignment. All right, so that takes us to the rational root theorem. If the polynomial p of x has integer coefficients, in other words, if it's a whole number for each coefficient, then every rational root of the polynomial equation p of x equals 0 can be written in the form p over q. And that's where p is a factor of the constant term of p of x, and q is a factor of the leading coefficient of p of x. In other words, if I have, we'll look at it here in our first example. But just write this portion of it down so far. So p, you're going to have to remember, is a factor of the constant term, and q is a factor of the leading coefficient. Okay, so here we have an example. It's 3x to the 4th minus 10x to the 3rd minus 24x squared minus 6x plus 5. Use the rational roots theorem to find all the possible rational roots of the equation. So first we start with what our p's could be. If you remember, it's p over q, and p is a factor of the constant term. The constant term is always going to be the one with no x. So what are factors of 5? What multiplies to give us 5? It could only be 1 and 5. Then we have q. What multiplies to give us 3? It could only be 1 and 3. Step 2, test the possible roots to see if it's a factor. So I found my p and I found my q, but remember we're looking for p over q. Also, additionally, it could be a plus or minus 1 and a plus or minus 5, because -1 times -5 gives us +5, which is what our p was. Same thing for q. Positive and minus 1, positive and minus 3. So now when I do my P over Q's, we're going to look at all the possibilities. It could be 1 over 1. And I'm going to list them out down here. That's 1. It could be negative 1 over positive 1. So we can leave this as plus and minus 1. It could be positive 1 over 3, or it could be negative 1 over 3. So this has a possibility of positive or minus negative 1/3. It could be 5 over 1 or negative 5 over 1. So that's a possibility of plus or minus 5 over 1, which is 5. Or it could be positive 5 or negative 5 over 3. So that's our last option, positive or negative 5/3. So these are all the possible values of P over Q. So now we're going to test the possible roots to see if it's a factor. How can we test our possible roots? Well, we can take the original equation and use synthetic division. So now we're going to test our possible roots to see if it's a factor, and we have to use synthetic division to do this. So we can start by putting a negative 1 in here, and then we're filling out our synthetic division chart. Negative 1 times 3 gives us negative 3. That makes this negative 13. Negative 1 times negative 13 is a positive 13. That's negative 11. Negative 1 times negative 11 gives us 11. Negative 6 plus 11 is 5. Negative 1 times 5 gives us 5. Negative 5. 5 minus 5 is 0. So whenever I plug the negative 1 in, that gave me a factor. So my first one is x plus 1. Now I can fill this out. My new equation would be 5, negative 11x, negative 13x squared, and 3x to the third. So now I'm still not done. I need to check multiplicity, or check for more factors of this equation. So I can try 1 again, or negative 1. What I will tell you is it's going to be a good idea to take this equation and plug it into Desmos to start with. So by plugging this equation into Desmos now, there's another method of doing this, which you guys can't do at home because I'm assuming a lot of you don't have graphing calculators. So we just found at multiplicity at negative 1, right? If I was to plug that back in and see if I can do it again, I would be able to. And I can see that this has a multiplicity of 2 simply because it comes down and touches and bends. So now I'm going to do this again, synthetic division, using the negative 1 and my new numbers from here. Because I don't know if I have multiplicity of 1 or of 2 or 4 or 6 or 8. So then negative 1 times 3 gives me negative 3. Negative 13 minus 3 gives me negative 16. That becomes a positive 16. That's 5. Negative 1 times 5 gives me negative 5. Gives me a 0. It tells me that x plus 1 is still a factor. So I'm going to get rid of that for a second here. So now I have x plus 1 as a factor from above. And now I still have x plus 1 as a factor, which makes sense because if we look at our multiplicity, it would have to be a multiplicity of at least 2 to get to this point. So now if I rewrite this equation, I have 5, negative 16x, and 3x squared. Now that I'm down to an x squared, I can use my quadratic formula to solve this. So that would be negative b, which would be negative of a negative 16, so a positive 16, plus or minus square root of b squared, it's negative 16 squared, minus 4 times a times c, all over 2a, which just becomes 6. So negative 16 squared gives me 256. Four times 3 times 5 is 60. So 256 minus 60 is 196 here. And that's over 6. The square root of 196 is 14, so this is 16 plus or minus 14 over 6. 16 plus 14 is 30 over 6, which is just equal to 5. So that tells me I have a root at 5. And then I do 16 minus 14, which would give me 2 over 6, which is 1/3. So this would then be, don't forget to switch the signs, x minus 5 and x minus 1/3. If I go back to my Desmos and I click my roots, I have negative 1 twice. I have 0.333, which is 1/3, and then I have 5 is my other root. Now, I'm going to have you do at least a couple problems doing the synthetic division, finding your possible rational roots like this. But, yeah, I'm going to have you do that. And then testing them out by doing this. Now, I wouldn't suggest just randomly choosing like I did, because you have Desmos to use at your advantage. So, find the root, negative 1. We know that that's a root because it crosses there, and put it into the synthetic division. Solve it out. You know it's a multiplicity of 2 just by looking at this. Solve it out that way as well. All right, guys.